Okay, good morning, everyone. That's hard. Who is sad? Okay, it's kind of hoping for a few more. But okay, who got rickrolled? Yeah, that's better. That warms me inside. Sorry about that, but I couldn't resist. I was going to prank you guys on April Fool's Day and forgot about it. So that's the best I could do. Okay, today we are going to go through the last few weeks, looking at ODEs, briefly mentioning counting, and also going back to graph theory as well. Go through some examples and just summarize the material. So this is a good opportunity. If you have any questions, please do ask. Maybe I'll leave it to the end. I've got a few, I guess, a few comments as well about like general approaches to stuff that might be helpful. Okay, so I'm just going to summarize stuff on ODEs to start with. So we first looked at linear systems of ODEs, and then we went on to look at nonlinear systems. And when we were looking at our nonlinear systems, we used all of our tools from linear systems by essentially linearizing our nonlinear systems around our equilibria. Okay, so you've already been examined on linear systems of ODEs, and you use the same tools for nonlinear systems of ODEs. So I'm not going to be examining you on linear systems of ODEs. Okay, so there will be nonlinear systems of ODEs on that. I can guarantee you that. Okay, so how do we analyze these? Well, the first thing we might want to do is find our steady states, same as fixed points or equilibria. So if we have, say, a pair of ODEs, the x dt is some function f of xy, dy dt is some other function g of xy. This could, say, be a predator-prey model or a disease model. It could be a plant pollinator, plant herbivore, mutualism, competition. Any of these things can be described by nonlinear systems of ODEs. To find our steady states, we're looking for values, pairs of values x star, y star, such that we have f of x star, y star equal to 0, and the same for g of x star, y star. Okay, so a common mistake that people make is that they find values of x star and y star so that this is equal to 0, or this is equal to 0, and then just put all combination of these two things together. These two equations have to simultaneously be equal to 0 to have a steady state. Okay. If you're not sure if what you found is a steady state, you solve your equations, you come up with some solution. There's an easy check you can do, which is just to plug the values. Say it was 1, 1. Plug those values back into these functions. If they're both not equal to 0, then it's not an equilibrium. Okay, so there is a check that you can do here to make sure that your answer is correct. Null clines. A null cline describes when one of our variables is not changing. Okay, so that means that either f of xy is equal to 0 or g of xy is equal to 0. Okay, so in this case, f of xy, if it's on our horizontal axis, if that's equal to 0, that means we have to be moving up or down on that null cline. And if g of xy is equal to 0 and y is on our vertical axis, then it means there's no movement up or down. We have to be moving left or right. Obviously, if you find your steady states first, for example, then this should give you your null clines as well. Okay, so you don't necessarily have to go all the way back through to find your null clines. It's worth noting as well when you draw your phase planes and you're looking at intersections of your null clines. If you have something that looks like this, where say you've got null clines on the axes and you've got something, in fact, I'm going to draw these in different colors. Suppose you've got a null cline that looks like this, and you've got one that looks like this, and these different colors represent null clines for our x variable and null clines for our y variable. So we draw one like this. You only have equilibria when there's an intersection of null clines for different variables, okay? So if I zoom in here, this is not an equilibria, it's not a steady state, because we don't have an intersection between a blue and a red line. this one is, this one is, this one is, and this one is, this one and this intersection here, they are not equilibria, okay? So just make sure that you're not accidentally finding equilibria where they don't exist. Okay, so direction field has caused quite a lot of problems to people. We know, I'll go through an example of this as well and talk about this in a bit more detail. So I'll skip over that for now, just because we're going to go through an example of that. Phase planes, like I said, sketch your null finds. Make sure you label your axes and label your null finds. Okay, if you don't label things, you're going to lose marks. In terms of steady state classification, we can classify things from our phase planes just by looking at the flow and where things are going. But we can also look at our Jacobian. So this is a matrix J, where we look at our partials. So on the first row, we have our partials with respect to x and y of our first function, f. And then on the second row, our partials with respect to x and y of our second function. And these are all evaluated at whichever equilibrium we're looking at that particular point in time. Okay, so you have a general Jacobian, and then you plug in your values for whichever equilibrium you're looking at. You could potentially just read off your eigenvalues straight away, and that might tell you something about the stability. So for example, if you have this in upper diagonal or lower, upper triangular or lower triangular form, so this entry and or this entry is equal to 0, then your eigenvalues are just going to be given by the elements on the main diagonal. And if you have lambda 1, if you have both of them, lambda 1 and lambda 2 less than 0, then you're going to have a stable node. If you've got one positive and one negative, you have a saddle. And if they're both positive, then you have an unstable node. Note that in this case, we can't end up with complex eigenvalues. You can read them off straight away. If you can't read them off straight away, or you're not sure about the eigenvalues, you can calculate the trace, the Jacobian, and you can calculate the determinant. We've done lots on trace and determinant, so you should be able to remember how to do those. And then you can also look at the sign of your trace squared minus 4 times the determinant. And looking at these three things here, that will help you classify. So whenever I say classify, I mean, don't just say whether something is stable or unstable, say whether it's a stable node or an unstable spiral or a center or whatever, okay? So this diagram here, you guys must be sick of this diagram by now. Just to make it clear what this diagram is showing, okay? If I find, for example, that I have a negative trace, that means that I am on this side of my graph, okay? If I then find that I have a positive determinant, that tells me that I am in the top of the graph, so I'm in this region here. I can't at that point distinguish between whether I have a stable spiral or a stable node. So that's when I look at the sign of this tau squared minus 4 delta, and that tells me which side of that red line I'm on. Common mistake that people make is they think if tau squared minus 4 delta is greater than 0, then you must be above the line. That's wrong. It's the other way around. Tau squared minus 4 delta being greater than 0 means that you are in this region here, or if you had a positive trace, you would be in this region here. Okay, so you're below the line. Reason being that if you can't remember which way around it is, tau squared minus 4 delta tells you whether your eigenvalues are real, in which case, if it's positive. If it's negative, then you have complex eigenvalues. You can only have oscillations if you have complex eigenvalues, okay? So tau squared minus 4 delta being less than 0 means that you must be in this region here, because this is the only region where you have some sort of oscillations going on. Another thing that a few people made a mistake on in, say, the IQ is the center. So this is when your trace is equal to 0 and your determinant is positive. Okay, so this center only applies to this region here, okay? We're above that red curve. If you have your determinant less than 0, it doesn't matter what your trace is, you always have a saddle. Okay. Any questions on systems of ODEs before I move on? Okay. Okay, the last part of the course was about discrete mathematics. We started off with counting. And we met 3 things when we looked at counting. We looked at, first of all, multiplication principle. So this is, for example, if you have independent events and you have a set number of outcomes for each of those events, how many possible outcomes can you have in total? We just multiply the possible number of outcomes for each event. So if I roll a dice that has 6 sides, I have 6 possible outcomes. If I then flip a coin or roll another dice, I would have 2 or, if I roll another dice, I have another 6 outcomes. So we'd have 6 by 6, 36. Or if I flip a coin, I have 2 outcomes, it'd be 6 by 2, okay? So there was an example before that confused quite a few people. If we have 50 individuals and they're being assigned to one of 3 treatments in a drug trial, how many possible ways can we do this? Each individual has 3 possibilities. So the first individual has 3 possibilities. The second has 3 possibilities. That's 3 by 3. The third has 3, and so on. So you have 3 to the power of 50. A lot of people ask, why isn't it 50 to the power of 3? That would mean that you'd have 3 individuals and you're assigning 50 possible outcomes to each of those 50 individuals, okay? So make sure you know the way around for these things. So there's multiplication principle. We also looked at permutations. And so if you have a set of n things, n objects, and you're drawing k of those things from that set, and you care about the order, then you can work this out as n factorial over n minus k factorial. So for example, if the key here is you're not remove, there's 2 key things here. You don't have repetition, okay? So things aren't getting placed back into that set, so they can't be drawn a second time. And that means that what you draw first affects what you draw second, and so on and so on. Okay. So if you have a group of individuals, it's say 10 people, and you're making a sports team that has 5 individuals on it, then you have your n here being 10, your k being 5. We don't care about the order in which we're drawing those individuals there. Okay, so permutations, sorry, you do care about the order. Stupid example. If this was a relay team, let's do the relay team example. Jumping ahead of myself. If this is a relay team and you care about the order in which those individuals are running, and you say how many different teams of 4 can we produce from that initial group of 10, that larger squad, then we're going to have 10 and 4. The example that I ran ahead with then of combinations is where the order doesn't matter. So if I was picking from that same group of 10 teams of 4, but I don't care about the order, then in that case, we would have what's referred to as 10 choose 4. So in its most general format, we write it as CNK, or in this bracket form here, which is read as N choose K. And this is just our permutation divided by k factorial. So just remember, permutations where you care about the order, combinations where you don't care about the order. Okay, we then moved on to graph theory, and in particularly looking at food webs to start with. And there are various definitions of trophic level and trophic status. So make sure you're aware of the distinction between these things and how you calculate, say, trophic status, how you calculate weighted trophic levels, okay? And talked about digraphs and compartment models. So there we should be able to move back and forth between a matrix, transition matrix, was P, and some entries in here. And if we think of the rows and columns of P as being vertices, say V1, V2, V3, then you can construct a digraph, or you can go from a digraph to a transition matrix. Remember that these are directed, okay? If you care about the directions here, you also make sure you label things. If I don't have any labels on here, then I can't translate this back and forth, okay? So make sure you put labels on. Okay, we also talked at the end about Markov chains and PageRank algorithms. So Markov chains are special types of these transition matrices where our columns now all sum to be 1. And these essentially tell us about the probability of moving from one state to another. Okay, so given today is, say, cloudy, there's a probability that tomorrow will be sunny or cloudy or rainy. We can write this down as a transition matrix. We can write it down as a digraph. And we can think about the eigenvector that is associated with the dominant eigenvalue. In these systems, you always end up, if it's a Markov chain, you always end up with your dominant eigenvalue being equal to 1. And you can end up with some eigenvector associated with that. And if you want to understand this in terms of fixed probabilities, or what's the distribution in the long term, you need to convert this into a fixed probability vector. And the key thing about a fixed probability vector is that the sum of the elements are equal to 1. So how do you do that? You sum up all the elements within your eigenvector and then divide through by them. This is normalization. And you end up with a fixed probability vector where all of the elements sum to 1. And that will tell you the long-term distribution of these different states. And that is everything. Any questions? Okay. I'm going to go through this example with you, rather than give it to you guys as an example to make sure that everything's clear. We've done a lot of systems of ODEs, but it has caused quite a lot of problems for people, so I want to make sure that it is really clear. Okay, so we've got some relationship here between two species, X and Y. We don't know what they are. The first thing we're asked is this relationship mutualistic, competitive, or exploitative? Okay, so how do I know this? Well, what we can do is we can think about what happens if we remove the other species. So if I just think about species 1, say, okay? So I have species 1 here by itself. What happens when I introduce species 2? Well, if I introduce species 2, the coefficient in front of this species 2, given by Y, is positive. So this is positive, which means essentially that Y provides some sort of benefit to X. I'm going to say helps in the very loosest sense, okay? So positive sign here means that Y helps X. I then do exactly the same for the other species. So cross out everything for X. I now have just Y by itself. And then think about what happens when I introduce X. This here is negative. So that means that X harms Y. Okay, it's reducing its growth rate. So for this to be mutualistic, we'd need both of these things to be positive. So they would both be helping each other, mutualistic, cooperative, same things. For them to be competitive, we'd need both of them to be negative, so they each harm each other. And exploitative means that one of these is positive and one of these is negative. So in this case here, I have an exploitative relationship. We can see that species Y, because it has the negative sign, this is the victim, and species X is the exploiter. So X could be a predator, it could be a parasite, it could be a herbivore. The victim could be a host or a prey or a plant species. Okay. Okay, so how do we, part B, find and classify the stability of the steady states? So let's work through this as an example. So first of all, I'm going to set f of x, y equal to 0. So what does that mean? Well, that means that either x must equal 0, this term here, or the thing in brackets, 1 minus x plus y over 2, must equal 0. I'm going to rewrite this here as, let's put it in terms of y. Y is equal to 2x minus 2, if I haven't made a mistake. Okay, so I've got these two conditions here, that for the first equation to be equal to 0, one of these two things must be true. Both of them could be true, but we need at least one of them to be true. So now at this point, I can think about my second equation. So when is g of xy equal to 0? Well, I either need y to be equal to 0, or the thing in brackets, 1 minus x over 2 minus y equals 0. Again, I'm going to rearrange this in terms of y here, see y later on. So I need one of these two things to be equal to 0. So we can now think about what happens when one of the conditions for the first equation is satisfied. What does that mean for the second equation? So if x is equal to 0, then dy dt is equal to y times by 1 minus y. So y must equal 0, or y must equal 1. So that's the first one. Now I can think of the second one. If y is equal to 2x minus 2, so that's this thing up here. So that's the second condition from the first equation. Again, I just substitute this into my second equation. This is a little bit more complicated. So we're going to have y, which is 2x minus 2. You have 1 minus x over 2 minus y, so we're going to have a minus 2x plus 2. That must equal 0. That is just this equation here being set to 0. Okay, so you can go ahead and solve this. You'll end up with a quadratic here. So we can tell immediately from this that we either need 2x minus 2 to be equal to 0, implies that x must equal 1, or we need the thing in the brackets here to be equal to 0. We're going to have 1 plus 2, so we're going to have a 3 minus 2x minus 5x over 2 equal to 0. Okay, so that's just this thing here being equal to 0. The first bracket being equal to 0 tells me that x must equal 1. And the second bracket being equal to 0 tells me that 3 minus 5x over 2 must equal 0. So if we rearrange this, we should get x is equal to 6 over 5. So now we've got these conditions here. At this point, we now need to substitute these back into our equations for y. So we have relationships for y here. And we have the other one up here. So we sub back in to find y. So if x is equal to 1, that was the case when we had y is equal to 2x minus 2. That tells me that y is equal to 0. 2 times by 1 minus 2, so we know it was y is equal to 0. And if x is equal to 6 over 5, I need to substitute it back into this equation here. If y is equal to 1 minus x over 2, if 1 minus 6 over 5 divided by 2 is going to be 3 over 5, which is 2 over 5. Okay, so that's quite a few steps going back and forth. At this point, I could go back and substitute all of these values in to check which ones are actually equilibria, or I can just work my way through them. So let's just summarize everything. It's kind of good to summarize everything at the end. So what are our equilibria? All the way back to the beginning. Well, the first one we found was x is equal to 0. And if x is equal to 0, then y is equal to 0 or y is equal to 1. Okay. So if x is equal to 0, y is equal to 0 or y is equal to 1. This first one here is known as a trivial equilibrium. The second is a semi-trivial. It's semi-trivial because one of the species is extinct. Okay, what else did we find? We found out that we could have one if x is equal to 1, then y is equal to 0. This is also a semi-trivial equilibrium. And then the last one we had at the bottom, x is equal to 6 over 5, y is equal to 2 over 5. And this is referred to as our coexistence equilibrium. Now, just because it's called a coexistence equilibrium doesn't mean that these species can stably coexist. Okay, at this point, you can find out if you want to classify the stability, look at the Jacobians. We've done quite a bit of that. I will upload the solutions for that, but in the interest of time, I won't go through those now. What I'll focus on instead is the phase plane. Okay. Again, because phase planes have caused quite a bit of quite a few problems. So I want to make sure it's clear. So first of all, set up your axes. And then the next thing you want to do is draw on your null lines. Now, I already know what my null lines are going to be because I've already solved these equations here. So the things that I'm going to, it's a bit messy now, so I'm just going to get rid of some of these things here. The things that I'm going to circle in green are my null lines. So that's a null line, this is a null line, this is a null line, and this is a null line. So I already found them when I was looking for my steady states. So for x, we have a null line when x is equal to 0. We also had a null line when y was equal to 2x minus 2. So that looks something like this. I'm not going to have my labels on here just in the interest of time, but you guys should make sure you label these things. Y has a null line, shown pink, when y is equal to 0, or when y is equal to 1 minus x over 2. Note that I'm only drawing these things in the positive quadrant, the first quadrant here. I don't need to look at values for x and y being negative because I'm interested in population sizes here, and we can't have negative population sizes, okay? So you don't need to worry about these other quadrants. So where are my equilibria? It's whenever there's a pink and green line intersecting. So we have 4 equilibria here. And I could jot on at this point what each of those equilibria are. For example, this is 1, 0. This is 0, 1. This is 0, 0. This is 6 over 5, 2 over 5. Okay. So let's now think about the direction field. And I think this is probably the bit that causes the most problems, but you know, it's okay. So what I'm going to do here is I'm just going to look at what goes on the axes. Okay. So first of all, let's think about the line x is equal to 0. That's my green vertical line. This is a null climb for species 1. So I know that dx dt is equal to 0. What is happening to dy dt? Well, dy dt is going to be y, 1 minus x over 2 minus y, and x is equal to 0. So this middle bit, we lose the x. So you substitute this into the equation here. So dy dt is equal to y times by 1 minus y. So this is going to be greater than 0 if y is greater than 0 and less than 1. And it's going to be less than 0 if y is greater than 1. And we don't care about values of y that are negative because y is the population size. So what does that look like then? If dy dt is positive, if y is between 0 and 1, we're on this axis here, so the arrow goes up when we're between 0 and 1. And when you have y greater than 1, the arrow goes down. Okay, now let's think about the other axis. So y is equal to 0. dy dt is equal to 0 by definition. So what's the change in my x variable? Dx dt is equal to x. That's by 1 minus x plus y over 2. Yes. Doesn't matter what it was because the y is going to be disappearing anyway. Y is equal to 0. We're substituting this into there. So just like above, this is going to be greater than 0 if x is between 0 and 1. And it's going to be less than 0 if x is greater than 1. So on that horizontal pink line, the arrow points to the right if we're between 0 and 1. And it points to the left if we're greater than 1. Okay. Now at this point, unless you're explicitly asked to find what are the direction field on all of your null lines, it will be the same process. It's a little bit more involved because we don't have one of the variables set to be equal to 0. You could go through this and do everything for those null lines. We can deduce what happens by thinking about the continuity of this phase plane. Okay, so what does that mean? That means that if I say zoom in here, and I move a tiny bit off this axis, and a tiny bit off this axis here, we're still going to be moving up, and we're still going to be moving to the right. Okay, and the same applies if I edge a little bit further over. Okay, so in this region here, I know that I must be moving up and to the right. That means that this pink null line, which remember means that there's no change in my y variable, so we have to be moving left or right. We can't suddenly be moving left, okay, because everything in this region here is moving right. That means that on this null line here, we have to be moving to the right. Okay, so we can deduce this from what happens on our axes, okay? Likewise, this green null line here, we know that in this region, we're moving up and to the right. So these arrows within here maybe look something like this. So this arrow on this green null line has to be moving up. Remember, green in this case means no change in my x variable. Okay, what else do we know? Well, we can go through all of the other regions and deduce it that way. We can also think about the fact that as we move through a fixed point, which is one of these black dots here, our arrows change direction. Okay, so imagine you're walking down this pink null line. Those arrows aren't the direction field, they're just indicating that you're moving along the null line. As you pass through that black circle in the middle, the arrow will change direction. Likewise, if I start down here, in this region here, as I move my way up this green null line, I pass through this black dot. We started with an arrow that was going up. On the other side, it's going to be going down. Okay. So you see from this that we were able to deduce, just by looking at the direction field on the axes, what happens everywhere else. Okay. So you don't necessarily have to look at the direction field on all of your null lines, you can deduce it by thinking of this continuity. Okay. So in this region here, we're going to be moving down and to the right. This region here, we're going to be moving down and to the left. This region, we're going to be moving up and to the left. So any of the trajectories that we start on, say here, we're moving down and to the right. It's not a very good one, actually. Let's do it from over here. Moving down and to the right. So we end up looking like this. Here, we're moving up and to the right. So maybe it looks something like this. And we can deduce from this that we have a stable node. Okay. Right, there's only about 10 minutes left. So I'm just going to go through food webs again quickly. So here we've got a food web. And we're asked to first of all calculate the trophic status of each species, and then ask if there are trophic status dominant species here. Okay. So how do we work out the trophic status? Well, we know that for our primary producers, grasses in this case, their trophic status is going to be 0. And then anything that eats just this one primary producer here. So rabbits only eat grass, so they have a trophic status of 1. Mice only eat grass, and likewise grasshoppers only eat grass. So those all have trophic status 1. Gets a bit more complicated as we move up the food web. How do we do this? So for the fox, we look at all the things that the fox eats. Okay, so it eats the rabbit and it eats a mouse. And we find the longest path. So the things that it eats directly obviously only have path 1. So we have 1 plus 1. So we're adding up these two things here. And then we look at the things that the fox eats. What does the prey of the fox eat? If I can say that correctly. Okay, so there's also a path from grasses to fox. And that goes through either mice or rabbits. Okay, so the grass's path could go this way and then here, or it could go this way and then here. Either way, it has a path length of 2. So we have 2 on here for the fox. So the fox has trophic status 4. Let's think about now the owl. So the owl, what does the owl eat? It eats a mouse. It also eats a frog. We can have a 1 plus 1 here. Those are the path lengths, the longest paths from those species to the owl. What has longest path 2? Well, there's this grasshopper here that has path length 2. So we're going to add on a 2 here. But note now there's 2 paths from grasses. So there's this shorter path here of length 2 through the mouse, or there's the path through the grasshopper, through the frog, into the owl. And when we're doing the trophic status, we always take the longest path length, okay? The longest path from grasses to the owl is 3. So owls have trophic status 7. I'll leave the snake and the hawk as exercises. I'll tell you what the answers are so you can check them. They are 7 and 14. Okay. So look at the species that it eats first, then look at and work your way down through the food web. So if I was doing the hawks, I would first of all say, okay, what does it eat directly? Snake, mice, rabbit. And then work from that downwards. Okay. Okay, trophic status dominant species. What does that mean? So if I just draw the rest of these on here, so we have 4, 7, frog was 3, and the bird is 3, snake is 7, hawk is 14. Trophic status dominant species, what we need to do is we need to first of all find the number of non-primary producers, but I'm going to just say non-plant species for these. So how many non-plant species are there here? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 non-plant species. And we say that a species is a trophic status dominant species if it has trophic status greater than 9. So there's only one species here that has trophic status greater than 9. 14 is greater than 9. So the only trophic status dominant species are hawks. It could be multiple trophic status dominant species. Okay, the last thing, it's not a question on here, but it's caused a bit of confusion as well about things that might happen and things that will happen. So if you're asked, for example, what will happen if, say, let's get rid of a species. If we said, what will happen if, say, rabbits are taken out? What will happen for certain? Well, the grasses lose something that eats it, so it loses a herbivore, or if it was a prey, it would lose a predator. We can also say what else will definitely happen. The fox will lose a food source. And these are things that definitely will happen. Beyond that, we can also say that hawks lose a food source because there's this arrow here, okay? So foxes and hawks lose a food source. Grasses will lose a herbivore. Essentially, the things that will happen are what happens if we remove these arrows. Everything else is speculation. Okay, so kinds of things that might happen. Well, if there are fewer rabbits around, or if there are no rabbits around, then maybe there's going to be more grass around. Maybe because foxes and hawks lose a food source, maybe there's going to be fewer foxes and hawks. The reason we can't say for certain is because maybe the foxes shift to eating more mice. Maybe if there's more grass around, that leads to an explosion in the mouse population, which ultimately drives the grasses down. There could be various reasons as to why these populations go up or down, and we can't say that without a full dynamical model. Okay, this is just a representation of the relationships. It doesn't tell us anything about the population dynamics. Okay. Okay, we've just got a few minutes left. Does anyone have any questions about any of the material or forever hold your peace? Okay. I guess before we go, I just want to say thank you guys. It's been a great class. It's been a lot of fun. Well, it's been a lot of fun for me. As much fun as you can have at 8:30 on a Monday, Wednesday, Friday morning. I know that for a lot of you guys that this is a compulsory class, and that means that you didn't want to take this class, but hopefully you've enjoyed or at least not enjoyed it along the way. If I could offer a couple of pieces of advice for things like the exam and also for future stuff. I've said a couple of times about making sure that you structure your answers like a bit like a story. Make sure there's a beginning, a middle, and an end. Like tell the person that's reading it what you're trying to do, okay? Random like numbers dotted over the page doesn't tell us what's going on. The interpretation questions, usually it's like students try to overcomplicate it, okay? It's usually just say what you see. These species coexist, or describe the path, what happens. The population sizes are going up or they're going down. How are they changing, okay? I would also say, I think that a lot of you guys are still probably treating this kind of class as a bit like school. And obviously you're now all at university. I assume most of you are still in your first year. When I say kind of doing school, it's maybe not embracing all of the resources that are available to you to study, okay? So obviously this is a lot more independent learning now than you would have at school. And so what I mean by this, embracing resources available to you, at things like office hours, there's been, the same, I would say 1% of the class has shown up to my Zoom office hours, a few more to the in-person ones. From what I hear from the TAs, most people don't go to the workshop. Again, it's the same kind of like 20 or 30 people. We're talking somewhere less than 10% of the class, okay? If we look around, there's supposed to be, 450 people nearly in this class. about half of the people show up roughly. Okay, so I'm not trying to have a go at you guys, but I think it's if you find that you don't do as well on the exams and you haven't used all of the resources available to you, going forward for your future studies, it's important to think about what you might have done differently, okay? Because university study is very different to school study, and I think a lot of people in their first year still treat these classes like school stuff, okay? But hopefully that's like some advice to think about for future rather than having a go at you, okay? All the best on the final. I'll see you in a few weeks. Farewell.